Good afternoon. Welcome to today's video about the nucleus. This is just going to kind of tie up some loose ends about things that we have not quite discussed about atoms or things that are worth going over again, and specifically the central part of the atom, the nucleus. So there's a lot of interesting physics that happens at the nuclear level. You guys know that the nucleus of any atom, regardless of element, is composed of both protons and neutrons. Those are the things that are found in the nucleus. There's, I guess, one exception to this, and it would be the simplest form of hydrogen. Hydrogen is the simplest element. There's one form of hydrogen that has only a proton as its nucleus and no neutrons. Okay, nucleus consisting of just one proton. We have a word that means things found in the nucleus, okay? Basically, it means the number of protons plus the number of neutrons, and that word is nucleon. So if you hear the word nucleon, it just means either a proton or a neutron, something found in the nucleus. So if you take a look at this picture right here, we have a very typical model of an atom. It's not exactly right because we know that the electrons are not actually in defined orbits like this, and the nucleus is not nearly this big, but we see that we have 1, 2, 3, 4, 5, 6, 7 nucleons, and because 3 of those are protons, 3 of those are positive, since there's 3 protons, the number of protons tells us the type of atom, the type of element this is. If you had your chemistry tables, you would look up your periodic table for chemistry, you would look up what has an atomic number of 3, and that would be lithium. So this is actually a lithium atom that is depicted right here. Now, something that always bothered me about the nucleus until I learned about this is you have a whole bunch of positive charges in there. There's some neutral charges as well, but the positive charges, what do we know about those? Why don't they all repel each other away? The neutral charges, I guess you could say that they're kind of like a buffer, but it's not like the neutral charges like attract the positive charges. That's not what happens. Instead, why don't these positive charges just kind of blow the whole thing up? It didn't make sense to me when I was learning about this. Why don't the protons all repel each other away? Okay? And one of the questions might be, well, why do you think they would repel? Well, we know about the electrostatic force. Electrostatic force is given by this equation, K Q1 Q2 over R squared, where Q1 and Q2 are charges. R is the distance between the charges. By the way, the distance between protons in the nucleus, it's very, very tiny, 1 times 10 to the 15th meters apart in the nucleus. That's a tiny, tiny distance. That's like, I mean, the radius of an atom in the first place, or I think the diameter, is 1 times 10 to the 9th. That's 10 to the negative 9th meters. That's a billionth of a meter. Protons are 1 millionth that distance apart from each other. This is almost inconceivable how small this is. In any case, we get from the reference tables that K is 8.99 times 10 to the 9th newtons times meters squared over coulombs squared. Q1 and Q2 are charges. It's just the charge of a proton twice. So I'm going to do this. I'm going to cheat a little bit. 1.6 times 10 to the negative 19th coulombs. That's the charge of a proton. I'm going to just do squared so I don't have to write it again. Divided by the distance between the protons. 1 times 10 to the negative 15th meters squared. So let's see what the force is that's repelling these protons apart. 8.99 times 10 to the 9th times 1.6 times 10 to the negative 19th times 1.6 times 10 to the negative 19th divided by 1e negative 15 divided by 1e negative 15. We get that the electrostatic force repelling these protons away from each other is 230 newtons. I want that to sink in for a second because that might not sound like a very interesting number, but like it's 2 protons. They're tiny. And they're repelling each other with this much force. That's like a quarter of the average person, a third to a quarter of the average person's weight. That is insane. These 2 tiny little things can repel each other that strongly. So what holds them together? This is a huge force for those tiny little protons. You might say, well, what about the force of gravity? That's attractive. Yeah, let's try this. The force of gravity is given by G m1 m2 over r squared. G is 6.67. Again, all this is from the reference tables. All this is what we've done before this year. Newtons times meters squared over kilograms squared. The mass of proton is 1.67 times 10 to the negative 27th kilograms. And since there are two protons, I'm just going to square that. Divided by the same distance, they're still 1 times 10 to the negative 15th meters apart, and we have to square that. Just looking at this number is less than this number is less than this number. I'm expecting this to be significantly less. Turns out that the force of gravity between two protons in a nucleus is 1.86 times 10 to the negative 34th newtons. That is, it doesn't really exist compared to this force. It is so much smaller. It is attractive, but there's no way that that force does anything when the repulsive force is this much. So, gravity can't hold this together. So the question is, what does? What holds this together? And the answer is a force that we have not talked about yet this year. There's another force, stronger than the electromagnetic force, or I guess equal in strength to the electromagnetic force, that holds these particles together. And it has an extremely creative name. Just kidding. It is known as the strong nuclear force. It's the nuclear force because it works in the nucleus, and it's strong because it is very strong. Okay, it holds these protons together. It holds protons and neutrons together in the nucleus. That is the only function for this strong nuclear force. But here's the weird thing about it. The range of the strong nuclear force. Why haven't we talked about this yet this year? Well, shouldn't it be important? Shouldn't we have learned about this during forces? And the answer is no, because we are never looking at just one nucleus. Okay, we're looking at bigger objects, macroscopic objects. The weird thing about the strong force is that the range is extremely short. It only works inside the nucleus. Okay, it basically is zero outside the nucleus. Its strength is basically zero outside of it. I like to compare this to like a T-Rex. A T-Rex that's right next to you is really, really scary. But if you're like, you know how the T-Rex has the little tiny arms? If you're like an arm's length or 2 arms length away from the T-Rex, it's not going to do anything to you, okay? As long as it doesn't come over, run and come get you. It's really, really strong. The strong force is like the T-Rex. It's really, really strong, but it has an extremely short range. I have a little picture in my room, someone printed out and put my face over it, of like one of those carnival strongman from like the early 1900s. They've got the gigantic shoulders, gigantic arms, usually handlebar mustache of some sort, the huge upper body, huge chest, and they got the tiny little legs. They're super, super strong, but their range is very short. They don't have super long arms. They got jacked arms, but they got super short arms. They can't really do anything around them, okay? Their strength is limited to right where they are. Okay, so we've introduced the strong nuclear force. That is what holds these protons and neutrons together in the nucleus and makes sure that they don't just repel each other out to infinity. We're going to switch gears a little bit, and we're going to talk a little bit about chemical and nuclear reactions. Really, we're going to talk about the difference between chemical and nuclear reactions, then focus on the nuclear side of that. Last year in chemistry, you focused on chemical reactions. Chemical reactions happen because of the movement of electrons between different molecules or between different atoms. That's what chemistry is. It's focusing on the movement of electrons. Nuclear reactions are different. They don't happen because of the movement of electrons. They happen due to changes within the nucleus, changes with nucleons. A chemical reaction, and it took me a while to understand this, a chemical reaction changes the type of molecules that are formed. Okay, that's what you studied all last year in chemistry. It changes the type of molecules that are formed, but chemical reactions do not change the types of atoms that are present. Remember, molecules are made up of atoms. Atoms are the building blocks of elements. An element has, like, the smallest unit of an element is an atom. Molecules are made up of multiple atoms. You can change what molecules are present in a chemical reaction. You can't change what elements are present. On the other hand, a nuclear reaction actually will change the elements present. what happens is either nucleons are added or subtracted, and that can change the type of elements that are there. I've got two examples here. This first one is a chemical reaction. We know it's a chemical reaction because even though we start off with H2, that's hydrogen, elemental hydrogen, and O2 is elemental oxygen, and they react, so we have two H2s and an O2, they react to form two different H2O molecules, so that's water. There's 4 hydrogen atoms in the beginning, 4 hydrogen atoms at the end. 2 oxygen atoms at beginning and end. This is a chemical reaction. The only reason that these atoms switched places, is because the electrons that they have swapped places. This, on the other hand, is a nuclear reaction. We see that we have actually 2 different types of, I know this is probably a little difficult to see. Let me see if I can get a better picture. We have 2 different types of hydrogen down here. We have deuterium and tritium. The only difference between the two, they both have 1 proton, so we know they're hydrogen. Deuterium has 1 neutron. Tritium has 2 neutrons. We throw them together, we smash them together with a ton of energy, and what we get out of it is not 2 hydrogen atoms. We literally get a helium atom out, and also an extra neutron and some energy. That's crazy. We literally changed the type of element that is there by doing a nuclear reaction. You need to know the difference between these. Chemical reactions are not nuclear reactions. They're very different. So, where do we do nuclear reactions? We'll talk about the different types in just a second, but first I want to talk about where we do these nuclear reactions. I mean, literally everywhere. Nuclear reactions happen in a lot of different places. Some of the most famous ones you might hear about in the news happen at these really big, really complex laboratories called particle accelerators. Particle accelerators, well, I guess they don't have to be huge. One of the ones you might have heard of is the Large Hadron Collider at CERN. That one is actually so big that it's in the shape of a circle. It's underground, and it actually goes under 2 different countries. It goes under parts of France and Switzerland. The diameter of this circle, this circular laboratory, is like 20 miles or something. It's absolutely huge. Basically what it is it's a bunch of underground tunnels through which scientists use really, really big electric and magnetic fields to accelerate nuclear particles, things that are in the nucleus, very, very fast until they collide with one another. So this might sound kind of silly. Okay, why are we colliding particles? Why are we doing this? Why are we pouring billions and billions of dollars into this? You know that if you take 2 golf balls and you collide them together, well, you're just going to get 2 golf balls out. Okay, that's all that's going to happen. Maybe if you collide them very fast, one of the golf balls busts open or one of them explodes, whatever. You're still going to have 2 golf balls, or at least 2 golf ball remnants. It doesn't work like that for a nuclear collision, for collisions between things in the nucleus, between subatomic particles. You could take 2. Let me give you this example. If collisions of golf balls worked like these nuclear reactions did, you could collide these 2 golf balls, and you might get a golf ball back out, but you also might get a ping pong ball out, you might get a brass mass, you might get a basketball, you might get a soccer ball, you might get a football. You'll get all these different types of particles that weren't there in the first place. If that sounds weird to you, you're right. It does sound weird. This is literally what happens when we collide nucleons together in particle accelerators. Instead of getting particle fragments after they smash into each other, there is so much energy involved in these collisions that the energy actually creates new particles that were not present beforehand. That is what particle accelerators do. They're really, really cool. And I should say they don't have to be enormous, okay? My college had a particle accelerator in the basement. Obviously, it wasn't 20 miles in diameter, but it would have fit like in the physics classroom, but we could still do experiments on it. The bigger you make a particle accelerator, the more energy you can use and the more interesting results you can get, essentially. But it was really cool that we had our own particle accelerator. So this picture right here is a readout from a collision that happened at this Large Hadron Collider at CERN over in France and Switzerland. Now, I'm not going to pretend I know what's going on here, but someone who works there would be able to look at the trajectories of all these lines representing particles coming out of this collision and be able to tell exactly what was created and what happened in the collision. I know I'm kind of being kind of hand wavy around this. I'm kind of saying, oh, all this stuff happens. It is so complex to explain what happens that you really need to study this and research this for years and years and years. You need like PhD level smarts and focus on this specific stuff in order to understand what's going on here. I'm just giving you the general overview. We use particle accelerators to understand the basic structure of nature. We use them to understand what is inside of these things like protons, neutrons, and electrons. If there is anything inside them, we can tell that, and we can look at how much energy we're putting into these collisions and what happens. And this advances our knowledge of how the universe is structured. Let's talk about nuclear reactions that are a little bit more common and ones that are more important for your everyday life. We can actually use nuclear reactions to provide energy. Okay? We use a lot of fossil fuel energy. We use a lot of renewable energy like solar, wind, hydrothermal, geothermal, stuff like that. Nuclear energy, energy from nuclear reactions, is another option that we have. There's two main types. You've heard of them before: nuclear fusion, nuclear fission. Currently, we know how to use nuclear fusion. Nuclear fission, fission, in nuclear power plants as a source of energy. Fission and fusion are kind of opposites of each other. Fission means you take a very big thing and you break it into smaller pieces. So you can see from this picture what's happening is you take uranium-235, that's an isotope of uranium. You shoot a neutron into it, and it becomes uranium-236. Okay, you've basically added to the nucleus. Now, what that does is it makes the nucleus unstable, and it will break into these pieces. It'll break into some barium, and also some krypton, and also some spare neutrons. It'll also release a little bit of energy, and that energy we can harness to power things like our houses. So, in a fission reaction, very heavy elements, that says heavy, are split into lighter elements. But this is bad. Okay, it's not bad that we're getting energy out, but it is dangerous. Dangerous waste products are released. It would be great if uranium-236 split into two useful things, but barium and krypton, like, we have no use for that stuff. And they're hazardous to your health. They're dangerous waste products. Okay, the reactor meltdown at Chernobyl, okay, in Ukraine, back in, I think, 1986. Basically, a nuclear fission plant overheated, and so much radioactive waste product was released that you still can't go near Chernobyl. If you go anywhere near there, okay, you have a chance of getting very, very sick very, very fast. Like, crazy amounts of radiation are still there that affect your cells and actually cause you to grow like tumors and have cancer and stuff like that. That's not science fiction at all. That's literally what happens. So fission, most of the time it's fine because we know how to control the waste products. However, it can be very dangerous. What we would love to discover how to do is how to use nuclear fusion properly. Nuclear fusion is fission in reverse. Instead of going from heavy to lighter elements, you take light elements and you smash them together to form heavier elements. The example on the front is the same example that we have here. Deuterium and tritium, smash them together, you get helium out, you get an extra neutron out, and you get energy out. This releases energy, but there's no harmful waste products. We can use helium. We have abundant amounts of hydrogen, okay? Literally just the world's oceans are full of hydrogen because it's full of water. So we can actually use fusion. If we can master how to get fusion, a fusion reaction going, we would never need any other type of energy. Okay? We could run most of our civilization off of nuclear fusion, and we would. There are basically no side effects. There are no consequences to this. It's clean energy. The issue is it's very, very hard to. It's not hard to start nuclear fusion. It's not hard. I shouldn't say it's not hard. We've figured out how to start nuclear fusion artificially. We figured out how to keep it going. The issue is it currently takes way more energy to start fusion. To start the fusion reaction than we get out of it. So it's just not cost effective yet. Matter of fact, one of my professors and in college was worked very closely with a lab out in California, which is aiming to be one of the first labs to achieve a sustained economical fusion reaction. By the way, nuclear fusion is how the sun creates its, I shouldn't say creates its energy, but how the sun derives all of its energy that we eventually get here on Earth to power everything. Okay, that's all nuclear fusion. Last thing I want to talk about with nuclear reactions, they also happen when certain isotopes, remember from chemistry, an isotope is a certain type of a certain element. It just has a different number of neutrons. Remember, elements are determined based on how many protons they have. Isotopes have the same number of protons but different number of neutrons. So you might have isotopes, like these are different isotopes of uranium right here. They just have different amounts of neutrons. When isotopes of elements undergo radioactive decay was discovered, or at least made famous, by Madame Curie. When isotopes undergo radioactive decay, they spontaneously emit particles or radiation, and they change into a different isotope or a different element entirely. The reason we're talking about this, because this is a chemistry topic from last year, the reason we talk about radioactive decay is because it is controlled by another force that we have not talked about yet. It's controlled by something called the weak nuclear force. Obviously, if we have a strong nuclear force, we have to have a weak nuclear force. The only thing you have to know about the weak nuclear force is that it does not act outside of the nucleus, and it controls radioactive decay. It allows for radioactive decay. That's as far I'm going to get into it as well as we're going to go in this class. It is the force that you could say is the reason for radioactive decay. So, now that we've talked about the strong force and the weak force, the strong nuclear force, the weak nuclear force, we're now going to talk about the 4 fundamental forces in physics. You might be saying, wait, we've done a ton of different forces this year. We've talked about like at least 10 different forces. It turns out that we can classify any force as being derived from 4 different fundamental forces: the strong nuclear force, the electromagnetic force, the weak nuclear force, and the force of gravity, the gravitational force. Now you might be saying, okay, well, what about tension? What about the applied force? What about friction, the normal force or spring force? All the forces that you have learned about prior to this video, minus the force of gravity, are extensions of the electrostatic or electromagnetic force. Take friction, for example. Friction is the force that, if 2 objects move past each other, friction kind of slows one of the objects down. That happens because objects are made up of charged particles. When those charged particles get near each other, yeah, they're going to repel each other a little bit. That might slow down the object. Tension, the force from a string, is simply the force of, well, first of all, the tension is the force from the rope that pulls on something. That rope is held together by electromagnetic forces. Same thing for a spring force. Springs are held together by electromagnetic forces. Normal forces. When you touch something, you are not really touching that object. You are just getting to the level where your hand, if you're touching it with your hand, cannot go any farther because it's being repelled. The atoms and the charged particles in your hand are being repelled by the charged particles in whatever you're touching. So if you ever play that little trick on your little brother or sister where you hold them or not that one, but where you say like, oh, I'm not touching you when you're a kid and you're trying to bother them, even if you were touching them, you're really not. Your particles are held at bay a little tiny distance away from the other particles due to the electromagnetic force between them. So everything that we have studied, almost every force, with the exception of gravity, has been a version of the electromagnetic force. The only exceptions, the 2 that we learned about today, the strong and weak force, those are, or were, seen as separate. So there's really 4 forces at play in the universe that we can talk about: strong force, electromagnetic force, weak force, gravitational. Their relative strength, the strongest one is up here. The strong force is the strongest. The electromagnetic force is a little weaker, but it's still pretty strong. The weak force, as the name implies, is weak. And the force of gravity is actually the weakest force, which is crazy because we think of gravity as like holding the earth together. Gravity only becomes a large force when you are dealing with huge masses, like at least the size of like a mountain. The range of the force, we've talked about these before. The strong and the weak force only act inside the nucleus. Whereas the electromagnetic and the gravitational forces are both proportional to 1 over r squared. In other words, the distance between 2 particles, the square of that and the inverse of that square is proportional to that force. In other words, these forces fall off as you get farther and farther away. But since you can never get this quite down to 0, like even if you put this at infinity, or basically infinity, there's still going to be some tiny amount of force. So there is an infinite range to both the electromagnetic and the gravitational forces, in contrast to the nuclear forces, the strong and the weak. Really quickly, what do these different forces do? The strong force, very simply, holds the nucleus together. The electromagnetic force holds small objects together. And by small objects, we're talking about anything from the size of an atom up to like the size of like our own scale, like a person, or even you could even go a little bit bigger than that, up till about like it would hold a house together, a building together, up till about like the size of like a small hill or a mountain. Those things are held together by the electromagnetic force. The weak force allows for radioactive decay, or controls or is the reason for radioactive decay. And the gravitational force holds big objects together. Anything bigger than, like, say, like a mountain, okay? So a moon, an asteroid, a planet, a sun, a galaxy. That's the role of all four forces. And again, most of the forces that we've been dealing with all year are just variations of the electromagnetic force. We can still use tension, spring force, applied force, normal force, friction, but at their core, they're just variations of the electromagnetic force. And you remember how we said, you look at this word, electromagnetic. People back in the day used to think electricity and magnetism were two different things. It was proven that they are actually two different aspects of the same force. So this got people thinking, especially because electromagnetic force, or electrostatic force, with its dependence on 1 over r squared, is the same dependence that gravity has on 1 over r squared. People start to think, well, hold on, can the electrostatic force and gravity be combined? Or what about the strong and weak forces? Can they be combined somehow? Are we missing some deeper connection? And it actually turns out that people who are particle physicists, who study things, who work at laboratories like CERN, like we talked about earlier, they are actively trying to show that under the right conditions, at very high energies and very high temperatures, these forces kind of blend into one another. They're just different manifestations of the same root force. They're trying to show that these forces are all actually the same, and just that in our everyday conditions, they look different to us. This is going to be, if we ever reach it, a key feature of the theory of everything, which can explain every physical phenomenon in the universe very simply. We have actually gotten to the point where we have unified the strong force, the electromagnetic force, and the weak force. We have proven that those forces all arise from the same root causes. They all come from the same thing. We just see different aspects of them in different locations. The one that we haven't unified yet is gravity. Okay? We're having a tough time trying to unify gravity. It might be impossible. It might be that there are just two forces in the universe. The one that combines all three of these forces, and then gravity is something separate. But we think we can combine all of them. We haven't gotten there yet. We don't have a unified theory of everything yet, but we're actively looking for it. And if you choose to study physics, there's nothing that says that you can't be the one that finds the unified theory of everything. Pretty sure you'll be pretty famous if you happen to do that. Okay, that just kind of ties up a bunch of loose ends on the nucleus. Our next video is going to be on the most famous equation in physics, the relationship between energy and mass.